Hello. In this video, we are looking at conformations of cyclohexane and cyclohexane derivatives. Here we have the optimized structure for methylcyclohexane in the equatorial conformation. We note that the carbon-carbon bond length from the methyl group to the ring is 1.532 angstroms. When the methyl group is in the axial position, the carbon-carbon bond length is 1.537 angstroms. When we compare the computed enthalpies of the two different conformations, we find that the equatorial conformation is lower in energy and that the axial conformation is 2.83 kcals per mole higher in energy. Here is the axial conformation of bromocyclohexane with a bromine carbon bond length of 2.023 angstroms. We mentioned in passing that when we have a halogen in the axial conformation, then we have two adjacent beta hydrogens that are anti-periplanar, thereby enabling E2 elimination reactions. We actually have the right orientation of the beta hydrogens, but only when the halogen is in the axial conformation. Here is bromocyclohexane in the equatorial conformation with a bromine carbon bond length of 2.007 angstroms. In the bromocyclohexane, just like the methylcyclohexane, we find that the equatorial conformation is lower in energy than the axial conformation. But in the bromocyclohexane case, the difference is only 0.88 kcals per mole. Here is chlorocyclohexane, with the chlorine atom being in lime green, and the chlorine carbon bond length is 1.851 angstroms. To repeat, the gray atoms are carbon and the white atoms are hydrogens. Here is the equatorial conformation of chlorocyclohexane with a chlorine carbon bond length of 1.839 angstroms. Notice that in each of the three cases so far, the equatorial substituent has a shorter length to the carbon ring than does the axial substituent. Again, as in the previous cases, the equatorial substituent, chlorocyclohexane, is lower in energy than the axial conformation, here by only 0.83 kcals per mole, but still with the equatorial preference over the axial substituent. For the remainder of this video, we are going to look at di-substituted cyclohexanes. Here we have the cis-1,2 dichlorosubstituted cyclohexane. When we have the cis-1,2 di-substituted cyclohexane, one of the substituents must be in the axial position and one must be in the equatorial position. Here is a trimmed view of the same cis-1,2-dichlorocyclohexane, showing that both of the substituents are on the upper side of the cyclohexane ring, therefore they are cis. Here is the trans 1,2-dichlorocyclohexane. There are two different possibilities when we have a trans 1,2-disubstituted cyclohexane. This is the first, where both of the substituents are in the equatorial position. Here we show a trimmed side view of the same trans 1,2-dichlorocyclohexane with both of the substituents, the green chlorine atoms, in the equatorial positions, and it helps to see the two hydrogens that are in axial positions. So it makes it easier to see the difference between the axial and the equatorial positions, and we can also see that the chlorine atoms are trans to each other. Here is the other trans 1,2-disubstituted possibility, where the two substituents, the chlorine atoms, are more clearly, in this case, in the axial positions. So for 1,2 trans, it can be either both equatorial or both axial, and in this case, they are both axial. Here is a trimmed side view of the trans 1,2-dichlorocyclohexane with both of the substituents being in the axial positions, and for comparison, we can see the attached hydrogen atoms that are each in the equatorial positions. Table 4 displays the computed enthalpies for the various 1,2-dichlorocyclohexanes, showing that the trans case, where both the substituents are in axial positions, is the lowest energy, followed by the trans case where they're both in the equatorial position, and that the cis conformation is the highest, but only by about 1.27 kcals per mole. Now we proceed to the 1,3-dichlorocyclohexanes, here showing the case where the cis case of both substituents being in the equatorial position. In this trimmed side view, again we see the cis 1,3-dichlorocyclohexane with each of the chlorine substituents, the lime green circles, being in the equatorial positions, and we can see the hydrogen atom in white being in an axial position for comparison. Here is the cis 1,3-dichlorocyclohexane, but now the two chlorine substituents in lime green are in axial positions. As we have been doing, we now look at a trimmed side view for the cis 1,3-dichlorocyclohexane with the two chlorine substituents, each in the axial position, one eclipsing the other, so it looks like there's only one there, but the other one is directly behind it. Here is the trans 1,3-dichlorocyclohexane, and we see that there's only one possibility here, one substituent must be in an equatorial position and one must be in an axial position if we are to have them trans to each other and 1,3 disubstituted. Here is the trimmed side view of the trans 1,3 dichlorocyclohexane. Notice that the chlorine atom to the top is in an axial position and the chlorine atom to the bottom is in an equatorial position, which is the only way we can have trans with 1,3 disubstitution. For the 1,3 dichlorocyclohexanes, the favored energy conformation is cis, with both of the substituents being in equatorial positions, which is similar to the case when we have a monosubstituent preferring to be in an equatorial position. The highest energy case is the axial-axial case, where we have that unfavorable 1,3 axial interaction. Here is the cis 1,4 dichlorocyclohexane. And we notice that to have a cis orientation, we need to have one substituent, the one to the left, in an axial position, and the second, the one to the right, being in an equatorial position. We notice that this 1,4 situation is almost identical to the 1,2 situation for disubstitution. Here again is a trimmed side view of the cis 1,4 dichlorocyclohexane. Notice that the chlorine atom to the left is in an axial position, whereas the chlorine atom to the right is in an equatorial position. Here is the trans 1,4 dichlorocyclohexane with each of the chlorine substituents in axial positions. For our final diagram, we have a trimmed side view of the trans 1,4 dichlorocyclohexane with each of the chlorine substituents, the lime green spheres, being in axial positions. When we look at the computed enthalpies for the various 1,4 dichlorocyclohexane conformations, we see that they're very close in energy, but the lowest energy is for the trans case with each of the substituents in equatorial positions, followed very closely by the trans situation where the both substituents are in axial positions. I hope you found this video to be helpful and informative. Thank you very much for your attention. Have a good one.